Hello, IB. We're looking at solids of a revolution here in 19D.1 and D.2. And we're really just looking at the area under a curve, but now taking that area and revolving it around an axis. And for IBSL course, we are just going to focus on the x-axis. However, if we think back to how we first learned how to integrate, we basically approximated the area by thinking of little slivers of the area under a curve and kind of making rectangles out of them. And then we realized, well, the smaller rectangles that we make, so if we make an even smaller one, and we have multiple of them, so these little slivers now even smaller, and we add up all the little rectangular areas, the smaller those rectangles are, the better approximation we're going to get. So now if we think about taking those same little slivers, those little rectangles, and we revolve them around the x-axis here, what you guys wind up getting is a cylindrical shape. So if I took this little sliver, whatever it might be, and I revolve it around, I'm going to wind up with the same little sliver on the other side, and you'll wind up with basically kind of a revolution here. All right. Oh, so we can see right here at the end this beautiful little cylinder shape. So if you think of a cylinder, remember a cylinder is basically a circle, so it's the area of a circle, so pi r squared, and then we multiply it by the width of the cylinder, or the height of the cylinder. So that gives us the volume of a cylinder. So what we're really thinking is, well, we know the height is really going to be now the width of the cylinder, so here's going to be our height, and then what in the world will our r be? So if we think of what your radius is, so your radius going from the x-axis out to the end of that rectangle, infinitely smaller rectangles that we'll be adding together to find the total volume. Well, this distance here is your y distance, or your f of x. So your y distance is going to be determined based on whatever your function is. So now if we piece those together, what you're really looking at is your height, again, being the width of these cylinders. Your f of x is going to be your radius. So now we have your radius, we have your height, and then we can think of, if we take infinitely smaller cylinders, so we'll take our limit as your h, that height goes towards 0, of, again, it is your pi r squared multiplied by h. So that pi remains. That's where that comes from. Your r is your f of x value, your y value, squared, multiplied by h. But remember, your h goes to 0 because we're infinitely adding together the smaller little cylinders. So your h is represented as dx. That technically will go to 0. And you have your f of x squared multiplied by pi. And we are going to integrate, because by the definition of an integral, we are adding together, we're taking the sum of infinitely smaller cylinders. So what you guys are actually looking at is the integral from a to b. So where do we start, where do we end? Of pi times your function squared with respect to x. All right, we just discussed this. Pi r squared multiplied by h, and that's how that gets replaced now that we have an actual area that we are rotating in terms of integration. So in your textbook, the actual definition here is when the region enclosed by your function and the x-axis and bounded by the vertical lines at x equals a and x equals b, you can find that volume of the solid by using pi multiplied by the integral from a to b of your function, your y value, squared multiplied or with respect to x. So think about different ways that these questions can be asked. If you only want half of a volume or half a rotation, then you could do half a volume. A quarter, a third, they all work the same way. So just to prove how this actually works, and we're going to use two methods here. We'll use integration, and then we'll also prove just from what we know about finding the volume of certain shapes. Find the volume of the solid formed when the following are revolved through 2 pi, so in other words, through 360 degrees. That's the reason why that's in the question, about the x-axis. So we have the integral from 0 to 3. We have our pi r, which is our 2x, because that's our function, squared with respect to x. So what we're really looking at here is pi multiplied by the integral from 0 to 3 of 4x squared with respect to x. So now I'll actually take the integral by taking the antiderivative, which is going to be x to the third divided by 3. So we'll get 4/3 x cubed. And we will evaluate between 0 and 3. Pi can again just stay on the outside because we're going to multiply our final answer by pi, so it just hangs out with us along this whole process. We have 4/3 3 cubed, so 3 times 3 times 3, and then subtract 4/3 multiplied by 0 cubed, which is 0. So what you were really looking at here, 27 divided by 3 is 9. 9 times 4, that gives us 36. Minus 0. So our final answer is 36 pi. And now we're talking about volume, so now we're going to be talking in terms of units cubed. So 36 pi gives us our volume for that shape. The area under the line 2x rotated or revolved around the x-axis through 360 degrees. So if you just take a look at this picture on the right here, if I did actually rotate the line y equals 2x, it would cross at the origin, a gradient of 2 over 1, and I wind up rotating that around the x-axis. What I'm actually looking at here is a cone. So if we think about our radius of 6 and the height of the cone as 3, because it goes from 0 to 3, so if this cone were repositioned, we kind of are looking at it this way, okay, if we rotated it around, then what you guys would see is actually we'd be using the volume of a cone. All right, so we got 1/3 pi r squared multiplied by h. So if we have 1/3 pi, and these are using our formulas that we've been using throughout the years, as 6 squared multiplied by your h of 3. So 6 squared, 36. The 3's will cancel out, and then there you go with your 36 pi. So you guys wind up seeing how with a similar shape with a familiar shape that we've been using for years, and we can find the volume just using a formula that we have been practicing for years and think about how that has been derived. We get 36 pi, and that matches our new idea of taking the integral for a full volume of revolution. Now in our last section, we were looking at finding the area between two curves. So now let's think about finding the volume between two curves. If you have two functions where one is the upper limit and one's the lower limit or boundary, you guys have an intersection point that you'd be finding an enclosed space, starting at A and ending at B. We would find the area by taking the higher y value function, right, and subtracting the lower y value function from it. So the same goes for volume. Since by definition you're finding the volume between the curve and the x-axis that's rotated 360 degrees around the x-axis. So if I have now a lower boundary and I do not want to include this space here, so I might have an object that has a hole in it, like a washer or a vase, something that has an empty center or hollow center, I want to subtract out that inside. So if I wind up taking the volume of the outside revolution, whatever shape that makes, and I subtract the volume of whatever the inside revolution would make, which would be this little bit under this line here, between this line and the x-axis. If I subtract that out, I'm left over with that space, which is kind of the outside of the shape, or it would be the shell of the vase, or wherever the metal is for the washer. So depending on what shape you're actually trying to set up and find the volume of, you'd have to be strategic with how you set up your upper and your lower functions. But really, our formula follows from the same conceptual understanding that we were using with our area between two curves. So we have two different volumes that we have subtracted, and the pi repeats with both, so we can factor out the pi and just take the integral from a to b of our first function squared minus our second function squared, separately squared, right? Remember, squares do not, I can't do f of x minus g of x quantity squared. That won't give you the same value with respect to x. So just looking through example 14, we see that in this example, they intersect at 0, 0 and 1, 1. So our a value would be 0, our b value would be 1. So we'd be taking the integral from 0 to 1 of our upper function, which is the square root of x squared, minus our lower function, so x squared squared, and multiplying by pi. All right, and if you do rotate it, look at this gorgeous shape that it makes. So kind of a fancy bowl, I guess is what that could make if they wind up touching at the origin and just rotating that upper bit. So for you guys to set up for class, you've got the shaded region between 4 minus x squared. So downward facing or concave down parabola that's been moved 4 units up. So that is this piece here. And y equals 3, which is just a horizontal line, constant function going through y equals 3, revolved around the x-axis. So think about what shape that's going to make. In my head, I think of a wooden bracelet or something like that. What are the coordinates of a and b? So first, needing to find the intersection. So where do a and b, what x values are a and b at, so that I can actually find the intersection and set up my integral. And then find the actual volume of revolution. So your higher function squared minus your lower multiplied by pi. Go ahead and set this up, try it, and we'll start with this one next class.